All right, let's just jump right into this explainer. Today, we're demystifying one of the absolute most powerful tools in all of mathematics, integration. Look, whether you're specifically tackling the Cambridge 0606 syllabus or you're just trying to wrap your head around calculus in general, integration can feel like this massive, insurmountable mountain. But we're going to break it down today. We're going to visually map out exactly how it works, why it works, and how you can master it without the usual headaches.
Now, learning new math concepts at this level, yeah, it can definitely feel like a bit of a struggle. But, as this quote reminds us, pushing through that initial discomfort is literally how we grow. So if your brain hurts a little bit today, well, that just means it's working. You're building new neural pathways, and you are for sure not staying stuck.
Let's ground this with a real-world scenario from our source material. Picture this. We've got Mita. She's a long-distance runner. If we only have her speedometer readings at various times during a race, meaning her speed is just constantly fluctuating up and down, how do you possibly figure out the exact ground she covered? You can't just multiply a single speed by time, right? Well, this is where calculus steps in. Integration is the mathematical engine that lets us calculate that exact total distance by accumulating all those tiny, constantly changing rates of speed.
So here is our roadmap for today's toolkit. We'll be looking at unlocking the reverse process, pinning down the constant, the definite integral, calculating curved areas, surviving the x-axis trap, and finally, we'll hit some advanced integration rules. Let's get into it.
Section 1. Unlocking the reverse process, playing the mathematical movie backwards.
Here's the absolute most crucial point to remember. Integration is not some crazy alien language that you have to learn from scratch. If you know how to differentiate, you already hold the key. Think about it. If differentiation breaks the function down into its rate of change, like turning distance into speed, well, integration simply builds it right back up into its total value. It is, quite literally, just differentiation in reverse.
Side by side, you can really see the exact opposite nature of the two operations. On the left, when you differentiate a polynomial, the rule is to multiply by the power and then subtract 1 from that power, right? So to reverse it for integration on the right, you do the exact mathematical opposite in reverse order. You add 1 to the power, and then you divide by that new power. It's perfectly symmetrical. Honestly, burn this simple 3-step mantra into your mind, and you're going to be able to integrate almost any basic polynomial function. Step 1, add 1 to the power. Step 2, divide by the new power. Step 3, add a constant plus c. So, say you're integrating x squared. Add 1 to the power, you get x to the power of 3. Divide by that new power of 3, you get x cubed over 3. And then tag on that plus c. But wait, what exactly is that c?
That brings us to section 2. Pinning down the constant, solving for the mysterious plus c.
So why do we actually have to add that pesky plus c at the end of our equations? Well, think back to differentiation. When you differentiate a constant number, like 5 or -20, it just becomes 0. It vanishes completely. So when we integrate, to go backwards, we have literally no idea if there was originally a constant there or not. Adding c gives us what we call a general solution. Graphically, this means you've got a whole family of parallel curves sliding endlessly up and down the y-axis. To lock it in place and find your particular solution, you need a specific clue. If a problem gives you a known coordinate that the curve passes through, you just substitute those x and y values into your integrated equation, solve for c, and boom, you've pinned down your exact curve.
Moving on to section 3, the definite integral, setting the boundaries. Enter the definite integral. Unlike the indefinite integrals we just looked at, which leave us with an equation and a mysterious constant, a definite integral actually has boundaries. It has an upper limit and a lower limit, which you'll usually see written at the top and bottom of that little integration symbol. Because we're looking at a specific interval, the math evaluates to a concrete, specific numerical value. And the absolute best part, by giving the integral a specific start and end point, we no longer need the arbitrary constant c at all. Because mathematically, it just simply cancels itself out when we do the subtraction.
And here is exactly how that calculation works. You integrate the function just like normal, using the power rules we talked about. Then, you put that newly integrated function into square brackets. You plug your top boundary, your upper limit b, into the x values of the function. Then, you plug your bottom boundary, a, into the function. Finally, you subtract the bottom result from the top result, top minus bottom. It's incredibly elegant and straightforward once you get the hang of it.
Which leads us perfectly into section 4, calculating curved areas. From algebra to geometry. That specific numerical value we just found, it actually has an incredible real-world geometric meaning.
Definite integrals calculate the exact precise area trapped under a curve between your two boundaries, a and b, and the x-axis. It's like a mathematical superpower. But it gets even better. What if you need to find the area trapped between a straight line and a curved line? Easy. You just integrate the top equation and subtract the integral of the bottom equation. And if the exam question decides to be tricky and doesn't give you the boundary limits, just set the two equations equal to each other algebraically. Solving that is going to give you the exact x-coordinates where the two lines intersect, providing the perfect limits for your definite integral.
Section 5. The x-axis trap. Beware the canceling areas.
Okay, pay attention because we need to talk about a classic examiner trap that catches thousands of students off guard every single year. When you use an integral to calculate an area that sits entirely below the x-axis, the mathematical result is going to be a negative number. Now, practically, an area can't be negative, right? A physical space is a physical space. But if a curve weaves above the x-axis and then dips below the x-axis, and you just blindly integrate from the very start to the very end in one single go, that negative area from below the axis is going to mathematically subtract from the positive area above the axis. They cancel each other out, and your total area calculation will be completely, catastrophically wrong.
So how do we actually survive this trap? 3 golden rules. Number 1, always, and I mean always, draw a quick sketch graph first so you can visually see what the curve is doing. Number 2, identify exactly the coordinates where that curve crosses the x-axis. And number 3, chop the area up. You literally must integrate the section above the axis separately from the section below the axis. Once you get the negative result for the bottom section, you just drop the negative sign, meaning you take its absolute positive value, and then you add it to the positive top section to get your true, accurate total area. Section 6, Advanced Integration Rules, expanding the toolkit. Let's equip you with the rules for when that standard power rule just won't cut it.
See, the basic rule of adding 1 to the power doesn't work for absolutely everything. For instance, if you tried on 1 over x, you'd get x to the power of 0 divided by 0, which, yeah, mathematically breaks the universe. So the list right here is your ultimate cheat sheet for handling complex exponential, logarithmic, and trigonometric functions. And you'll notice a really beautiful pattern here. Because of the reverse chain rule, we are almost always pulling out a 1 over a at the front of these expressions. The integral of e to the power of something stays e to the power of something, just multiplied by that 1 over a. Sine turns to negative cosine. Cosine turns to positive sine. Secant square turns to tangent. Seriously, pause the explainer right now and take a screenshot of these formulas to use as a study reference.
And one final, massive red flag before you wrap up today. If you are evaluating a definite integral that includes sine, cosine, or tangent, your calculator absolutely must be set to radians, not degrees, radians. Calculus with trigonometry inherently relies on radian measure. If you accidentally plug in degree values, your final area is going to be completely wrong, and all your beautiful algebraic integration work will go straight down the drain. Always, always check for that little r on your calculator screen.
And that brings us to the end of our roadmap. We've seen how integration acts as a kind of mathematical time machine, taking shifting, temporary rates of change and building them up into concrete, total amounts and real-world geometric areas. Now that you hold the power to reconstruct the whole from its shifting parts, the real question is, how are you going to apply this mastery to the problems around you? Thank you so much for watching this explainer. Keep practicing those rules, and I will see you in the next one.